All right. So ideal gas law is going to look at one kind of snapshot of a gas. Okay, we're going to be able to look at temperature, pressure, volume, and the number of moles of a particular gas at one time. Okay, so thus far we've looked at Charles Boyle's, Guy-Lussac's, and the combined, which take a kind of before and after shot of a gas after a change. This is without any sort of change. This is just looking at a gas at a certain point in time. Okay, so we're going to start looking at ideal gases when they maybe aren't at STP. They have different conditions. It says PV equals nRT. We know three of those variables that we've talked about before. There's two new ones, the N and the R. Okay, these are what they stand for. Our new ones right here, N is going to be the number of moles of a substance. So N is going to be in moles. That will be its unit. R is what we call the universal gas constant. And that's a given value that you'll always have. Okay, the universal gas constant never changes dependent upon the particular gas itself. There's not a different gas constant for oxygen and hydrogen. It's the same no matter what type of gas you're looking at. Okay, and these are the universal gas constants right here. There's two different ones. Both of these are just called R, and there's two different values for them. Why do you think that they have different numbers? Look at the two and see if you can determine why there might be different numbers for each of those gas constant. What? No, not to confuse you.
Different units.
Different units. Look at the units that go with each of these. Okay, the first R is 0.0821 liters atmospheres over moles Kelvin. The second uses decameters cubed, kilopascals, moles, and Kelvin. Which of these, the top or the bottom, would we most likely use, do you think?
Top.
The top, because those are the units that we like to use. Liters, atmospheres, moles, and Kelvin. Okay, so that's why I've been working so hard to get you guys to convert everything to liters, Kelvin, and atmospheres. Okay, is so we can use this gas constant. Okay, so every time we use this ideal gas law, we've got to have our variables in those units. Okay, in order for R to work, this gas constant to work, it's got to have the correct units surrounding it. Okay? Okay, so this is R and how it came about, kind of. All right, so if we wanted to take PV nRT and rearrange it to solve for R, this is the equation that we would get. Okay, we divide NT over, and we get R by itself equals PV over NT. If we take very standard units, like 1 atmosphere of pressure, 22 liters is equal to 1 mole of any substance, right? We know that from Avogadro's principle. 1 mole of any gas is going to be 22.4 liters. So there's our number of moles, there's our volume. Temperature at STP is 273. If you plug these into your calculator, 1 times 22.4 over 1 times 273, you're going to get our gas constant out of that. Okay, so that's how they calculated R. The value is different for the second or the other R because they use decameters cubed and kilopascals instead of atmospheres and liters. Okay, so that's how R came about. We have to have these 4 units in order for this R value to work. Okay, so this will be a value you need to maybe put a star by in your notes or highlight it. You'll use it pretty often. Okay, we use the ideal gas law versus the combined. Okay, the ideal gas law only gives us one of each of the conditions. It doesn't give us an initial and a final pressure. It doesn't give us initial and final volume. You only get one of them. Volume, pressure, temperature. You only get one of each of those. And you get the number of moles, maybe, or you're solving for the number of moles. We don't use moles at all in combined Charles or Boyle's or Guy-Lussac's law. Okay. R is going to be a constant, so you use it the same number every single problem you do. You don't ever have to change the R value. You won't ever have to solve for it. Okay. The gas constant R won't be given to you in a problem. It won't be listed as one of your knowns. You'll have to just remember that and plug it in. Okay, it's not going to tell you the volume is this, the pressure is this, the R value is this. You have to just know that and plug it in. Okay, so it'll kind of look like you're missing 2 variables, but really you're only missing 1. Okay, you'll be given everything you need to except for 1 variable, and that'll be the one you're solving for. All right, let's try some. So it says we want to calculate pressure. We want to find pressure, so that's going to be our variable that we're looking for here. So we'll just give our P Question mark. What's the 0.413 tell us? What variable? N. Yeah, that's our number of moles, so 0.413. Oops. Okay. Does it matter to us that it's helium? No, it doesn't make a difference. Okay, it doesn't make a difference as far as our math or anything like that. Okay, so temperature is 16 Celsius plus 273, which is, I think, 289. All right, and our volume is 3.25 liters. Do we need to convert that to anything? No. So we have liters, we have moles, we have Kelvin, and we're going to solve for pressure, which will be in atmospheres, which is what we need in order for our R to work. So PV equals nRT. We're going to solve here for pressure, so we'll just leave a P there. 3.25 liters is our volume. N equals 0.413. R is 0.0821. And temperature, if I can fit it in here, is 289. Solve that whole right side, and then to get P by itself, you're going to divide over the 3.25.
ATM.
3.015 ATM. Okay, and we wanted our answer in atmospheres. We don't have to convert anything. Okay, we know that it's going to come out in atmospheres because that's what our R value tells us. In order for R to work, pressure has to be in atmospheres. Okay, so whatever variable you're looking for, just use that particular one's unit that we needed for R. Okay, good. Any questions on that one? Okay, let's try another one. Find the volume of 85 grams of oxygen at 25 degrees Celsius and 104.5 kilopascals. What do we do with our grams of oxygen? Yeah, we just convert to moles. That's it. All right, so how many moles of oxygen is that? 2.65. All right, so that's going to be equal to our N. Our temperature is 25 plus 273, which is 298. And our pressure, which if we convert 104.5 kilopascals, divide that by our 101.325, and we should get about 1.03 atmospheres. Do we agree? Take your 104.5 kPa, and then we're going to do a little T-chart to go to kilopascals to atmospheres. Okay, so you just divide that. All right, so I think that gives us about 1.03 atmospheres. Okay, so now we're going to go ahead and plug in and solve for volume. So our pressure is 1.03. Number of moles is 2.65. R is 0.0821. And temperature is 298. All right, so we're going to solve this whole right side. Then we're going to divide it by the 1.03 to get V by itself, which means our final volume should be what? 62.9, or about 63 liters, somewhere in there. How do we know it's coming out in liters? Yeah, that's what our R value tells us. We've got to have it in liters. Okay. Okay, try this one on your own. We're going to end up solving for pressure, and they want pressure in millimeters of mercury at the end, so that just means a conversion at the end. This is about what we got for atmospheres, 3.48. Okay, so then to go from atmospheres to millimeters of mercury, we're going to multiply it by 760, which equals about 26. 44.8, somewhere in that ballpark.